And we're recording. Hello there, Curious Clan. This is Sander at ABC, and thank you for joining me on here today. I thought it would be fun to try something a little different this week with an interview. It's a fresh format, but it's the same kind of geeky content that you're here for. And I could not have picked a better story to start with. It has Nobel Prize physics in it, it has a startup in my own backyard in it, and it has one of the hardest problems in chip making in there. So let me set it up for you. For years, chip makers have been checking their work with something called optical metrology. Basically, they put a light beam on a silicon wafer and then read what bounces back. It can tell you something about the tiny structures on there or about how well the layers in a chip line up. But today's most advanced chips consist of billions of these tiny structures across dozens of layers and with all kinds of funky materials. They are essentially skyscrapers, but at a nanoscale. And here's the thing: ordinary light can no longer see inside them. And while chip makers work engineering miracles, they can't build what they can't see. So, last week, a startup in Eindhoven raised 20 million euros to address exactly that challenge. Their answer is not better light, it is different light, shorter wavelength light, soft X ray. It's the same family of physics that won the Nobel Prize in 2023, and now they're trying to take this technology out of the chip lab and turn it into a machine that runs all day in a chip fab. My guest today is Dr. Christina Porter. She's a physicist and the co-founder and chief executive of Envisix. Christina, welcome to Always Be Curious.
Thank you so much. It's wonderful to be here.
Great. Well, let's kick off with a little bit of a background. Tell us a little bit about yourself, and where you come from, and how you ended up in the chip industry.
Yeah, certainly. So I'm Christina. As your lovely introduction mentioned, I am the CEO of Envisix, but I am a physicist. So I have a very nerdy background for being a CEO, but have been sitting here in the Netherlands working on the subject of this company for 7 years, 7.5 actually, and have been working on the subjects of soft X-ray metrology in total for 12 years now. And for me, that work started in the United States. So I am an American. And that work began at the University of Colorado at Boulder, where I had the pleasure of working in one of the sort of two pioneering groups on this light source called high harmonic generation. I was working in the group of Margaret Mernan and Henry Captain there. And at the point when I was with them, basically, we could make these short wavelength photons. And then we were trying to figure out what to do with them. And so back in 2014, we started reconstructing semiconductor samples by pairing this short wavelength light source with lensless imaging algorithms to reconstruct chips in 3D.
Right.
And this basically drew the attention of ASML. That is where the link to the semi industry began for me. Some of our senior fellows came and visited our lab in Colorado at the beginning of 2015. Um,
Hmm.
yeah, and I had the pleasure of pitching to them this application. So basically, Ari Denbuff, one of the ASML fellows, was there, and I showed him this thing in our lab, and it seemed to be interesting enough that this was one of the things that really started and interested ASML in making a program internally on short wavelength metrology.
Right. And the work at University of Colorado was as a PhD candidate, or
Yeah, indeed.
right? Okay. So, and how did the pitch go?
It was nice. Ari is one of these wonderful, curious people in the world, right? So, there could be nobody more fun to explain your science to. And they basically wanted to actually come down to the lab and physically see the thing, and then they had the impression that, it could be something really reasonable to industrialize. I think that was always
Right.
the question. Yeah, like, does this have the right outlook towards being a tool and not just a science experiment? But yeah, this somehow I was always interested in seeing if we could take this thing out of academia and into this, real setting. I think applied science, where you really have an impact on people's lives through products, is a very cool direction to go. So yeah, that basically started my friendship with ASML, and uh, then that blossomed into me wanting to come over to the Netherlands and join the effort here at the beginning of
Right.
2019.
Cool. So you came over to Veldhoven then.
Yes, indeed. I had the sort of dream of seeing this through from being an academic idea on an empty table to a real product, and I wanted to also move to Europe, so that there was a lot of yeah nice yeah just turned out to work well that ASML was in the Netherlands, and that they were actually interested to work on this, and so that's what I decided to do. Moved here with my husband, and yeah, spent 7 years internally at ASML working on this.
Wow. And what was it like to start building out that research program in this? Well, I mean, it's fast paced, dynamic, rather big, right? Company. So, what was that like?
Yeah. So, well, research is, of course, this small area in a huge company of ASML, which got much more huge over the years. But research is where we began with this program. And then over time, we moved into the development and engineering organization, and we grew a whole lot. But yeah, in the early days, it felt, very, very researchy. We were having to convince ourselves that you could not just make a single one shot picture on a camera every so often, but that you could actually, get enough automation into a tool like this that you would be able to measure consistently and actually like do an application and not just quick science experiment. So that was the
Right.
early years, trying to make a first tool that could do metrology, and then trying to figure out really what it was for. So, of course, this was a clearly at high level, right? What we say is soft X-ray metrology is good because it has enough resolution to see all of the details of these 3D geometries.
Hmm.
But specifically, the question was, like which layers, which specific devices, what particular applications are going to be the right ones. And so we spent some years at ASML figuring that out,
Right.
working closely with customers. And yeah, that was a great learning experience, and it helped us to really get sharp what we should focus on.
Yeah. And then at some point, you sort of you had the idea. Well, I mean, this first prototype tool that went into our R&D organization, right, and started really engineering it out. That could blossom into something that you would drive with your own team.
Yeah,
How did that come about?
yeah, yeah. So, well, as I said, basically, first we had to figure out what the tool was for and understand ourselves, like what is the real application area with customers, and then we began, to develop this first system that could be shippable. And then, I began to want to pull this program out of ASML, and actually do it independently in 2023.
Right.
Basically, with the observation or the reading, in this case, it was my group leader at ASML gave me a copy of the Innovator's Dilemma, and I, could see very much in our experience there. And that's a book that basically says if you want to make something really disruptive, then the right way to do it can be to step out of the parent organization that you're in and to build it up in an organization that's basically tuned to be really lean and be able to have all of its processes specifically designed for whatever really new thing that you're building. And basically, at the beginning, any new thing seems like it's small and uncertain, and it's really challenging to compete with the megalith like lithography. But that can be done very well sometimes if you actually do pull programs like this out of parent organizations and into their own sort of startup setting. So that was basically when I began to want to do this myself.
So a couple of years in then, and well, like I said in the intro, right? Successfully, you've secured some funding for your next steps. But before we dive into the future of this technology and the company Visix, let's also dive into the tech itself, right? So can you explain what soft X-ray metrology is and why it matters to chip makers?
Yeah, totally. So, conceptually, it's really simple. Conceptually, we just go to shorter wavelengths, and then we just get back enough resolution to be able to see inside these complex 3D devices. And in our case, the sort of neat thing about how we do that is we use a light source that you cannot just go buy at the laser shop. So it is this thing called high harmonic generation, which is a laser-like light source. But
Hmm.
actually, what is done is we take an intense femtosecond drive laser with enough energy in the pulse to rip electrons off of a noble gas that we focus into. The electrons go surfing on the drive laser field. They gain kinetic energy, and if they get well, they do get driven back towards their parent ion when the field flips sign. And if they recombine, they have to do that at higher energy out. So what you happen to get is, because of quantum mechanics, this comb-like spectrum of
Hmm.
colors at odd,
Rainbow.
yeah, a rainbow of colors at odd harmonics of the drive laser wavelength. And that is basically in a plateau out to some cutoff energy that depends on the drive laser wavelength and the gas that you're using. So this is this nice light source in the sense that it is really having a laser-like beam property. So it has a low divergence, and it is naturally multicolor. You don't have to do anything to get the rainbow. And those two things make it very convenient for a metrology source. Because in metrology, you usually want to focus some light onto a really small area of a wafer, and having a laser like beam is very convenient for doing
Mm.
that focusing. You don't need a really complex illuminator to collect all of your light. You can do it quite simply. And the many colors are bringing diversity of information. And it is
Uh,
diversity of information that's basically how you can have enough, yeah, signal, enough information to reconstruct the full detailed 3D geometry of a device. And we get that diversity for free, so we don't have to scan anything with this light source. It is just kind of yeah, there in the beam.
and the harmonics is born out of the work of Anne Lehulier, I guess, right? So she's a pioneer in the field, won her a Nobel laureate as well. Um, but she was in Lund University, if I'm not mistaken.
Yeah, yeah. So, well, high harmonic generation is something that was explored in academia for like 25 years
Mm.
before it ever had a life in industry. And there are multiple groups that really worked on it. Anne was one of the pioneering ones, and she had the pleasure of getting the Nobel Prize. Yeah, well, together with two others.
Yeah.
And then, yeah, Margaret Mernan's group in Colorado was also one of the leading and pioneering groups. So these two kind of amazing women brought this thing sort of to a level that it could conceivably go into an industrial setting. And yeah, Anne indeed was uh, hugely instrumental in our source development as well as ASML. We were collaborating with her group basically from the beginning, and she was helping us to, yeah, optimize the conversion efficiency of this thing and figure out, how do you do it really really well, and
Mm.
if it so that you have enough power to go to necessary throughputs in industry.
That's so
Um,
interesting because I mean, in her, she's of course a yeah, understanding the fundamental science, but you're at work at trying to bridge this towards engineering, right?
yeah, yeah.
But the two help each other.
Absolutely. Yeah, totally. I mean, and I think, well, yeah, many scientists, dream of getting to have a thing actually be industrialized or
Mm.
actually be used for something. So in that sense, there was a lot of joy, I think from Anne's side to work together, and yeah, from our side to have the deep basis of understanding and the ability from first principles to predict how these sources are going to work and to understand their beam quality. All of these things are enabling you to actually take a technology to a level that is high enough to be industrialized. So these things work
Right.
really beautifully in collaboration, I think.
Back to that rainbow and sort of high signal, right, that you were talking about. What is it that soft X-ray can see that, optical metrology light fundamentally cannot?
Yeah, yeah. Yeah, so, the thing that you're trying to do, when you're trying to reconstruct some device, is typically, you're trying to optimize a model of that device that has a whole lot of parameterized knobs on it, that allow you to adjust in your simulation setting, the geometry to cover a huge range of possible device, uh characteristics or shapes that might be on the wafer. And as devices have lately become really 3D, you have to have an increasing number of parameters to draw one of these things, right? Just like think about how many widths or heights you would have to draw to define uh, a small skyscraper. It's a lot.
Right,
And the problem when you are using light that has a very long wavelength is that basically all of the signals coming from all of the individual parameters of that device begin to look increasingly the same.
mm,
Uh, so it's not so much that you can't see something change in your signal when some device geometry parameter changes with visible light, but the issue is that if the signal coming from nanosheet number one changes, or the signal coming from nanosheet number two or three or four changes, they all look almost identical.
right.
So
You
uh,
wear blurry glasses and everybody looks the same,
Yes,
basically, right?
yes.
It's kinda
You
like
see
that.
something moving, but you can't really tell, uniquely, is it Bob or is it Jane? Like, who's walking over there?
Right.
Uh, so, yeah, that is basically the pain, today. It's this thing that we call, yeah, correlation in our signals,
Mm,
uh, for visible light. And, of course, also signal strength is painful, right? So the signals are really, really weak as well, but the correlation, I would say, is the most painful, issue. And yeah, the thing about soft X-ray is that it just sort of beautifully is able to decorrelate the signals coming from different device parameters because, well, one, we have the resolution to see them, and two, we have basically single scattering, which is a physical property of just how the light interacts with the device at these
mhm,
wavelengths. So we've got relatively weak scattering, and that means sort of you can think of it as interfaces don't really talk to each other too much. So like the fundamental signal coming from this one is sort of different than the fundamental signal coming from this one. And
right,
that's convenient. And so yeah, we can basically shine on these super complex 3D geometries where yeah, visible gets confused, and we just then have enough information to decorrelate all of these many parameters, and we can measure more parameters independently. Is our expectation with soft X-ray than with
right.
visible.
And you mentioned it was, lensless, right? So that means that software, is increasingly important. Is that what is if you were to look at the technology as it is now, what is the harder, problem to solve? Is it, hardware driven or software driven?
Yeah, yeah. So well, first we should say we are really 50% a hardware company, 50% a software company, and software
Yeah,
and
okay,
algorithm. So truly we have one foot squarely planted in each zone, and you have to do both, right, to have a real product. And neither is easy, of course. So I personally sleep pretty well at night over the hardware, also because ASML is an amazing background for building hardware. So ASML is specialized in making EUV hardware tools, and that means that
yeah,
they have all kinds of knowledge about how you do the optics and how you keep such a tool, yeah, stable and so on that we are able to leverage. So
right,
um, the hardware is far from easy, but let's say I think it's in our case something that we're pretty confident in. I think the algorithm and software side is not to be underestimated. So you have to work pretty hard to make a tool that is not only capable of solving the physical problem, and I think we have pretty well convinced ourselves that we can solve the physical problem, but to have it be user friendly enough that a customer actually wants to interact with it, and to solve problems fast enough, and to have a quick enough time between a customer handing you a use case and you handing them back a recipe that really works, like that is a relatively
Mm,
significant challenge. So, yeah, we are putting a lot of focus there as a company, and we do not at all underestimate the importance of the algorithm side and the importance of the software side.
right. And speaking of customers, the chip makers of this world, right? They don't buy a tool because the physics is elegant or there's a Nobel Prize involved, but they buy it because it makes economic and technical sense, right, for the process that they're building out. So where does soft X-ray fit in the chip making process, and what's then needed to bring it to high volume manufacturing?
Totally, yeah. Indeed, this is not a scientific activity. This is only making sense if the economics are right. And in general, you will not be adopted unless you are solving a very real pain for your customer. So that very real pain today is about, yeah, on the one hand, the fact that our customers just can't see stuff they need to see. And on the other hand, about the fact that the only sort of workarounds involve destructive measurements. So they usually
Ah,
involve cutting a lamella, a thin slice of device, and then sending electrons through it in a transmission electron microscope. So that is causing you to scrap a wafer. It's really expensive. It's really slow.
yeah.
And the fact that this hugely increasing amount of TEM is becoming necessary to calibrate, even to some degree, visible metrology tools is where, yeah, the pain point lies. So theoretically, visible light is cheap and non-destructive, right? But when you include all of the calibration, then that stops being true. So this became a drama in 2024 as gate-all-around devices became the way of the world in logic land.
Yes.
And yeah, if we already had a tool on the market today, our customers would be using it for gate-all-around today.
Mm,
Um, but the next huge thing that's going to happen is, right, so what we did with transistors is first laterally shrink them, and they were sort of individual walls, and then we rotated 90 degrees to make these gate-all-around devices. And the next step is that we will stack N devices on top of P devices. This is called a CFET
CFAT.
device.
Yeah.
And that additional factor of 2 in complexity is just extremely painful or really impossible for visible light to handle. So
Right.
we sort of really want to be there in time for the transition to CFET, but also, yeah, I would say if we were there earlier than for gate all around, there is also quite a large library of use cases that we see all of our customers agree that the pain is too high today
Mm,
to really be comfortable with current solutions.
yeah.
And then, yeah, something relatively similar is happening in the world of DRAM, where, yeah, we're moving from things like the 6F squared to 4F square architectures, and devices rotate again 90 degrees, and they get increasingly complex in this depth direction. And
Yeah.
yeah, there's just not suitable signal with visible anymore. So these are the application areas where we see, yeah, a lot of pull. And then obviously your tool has to be fast enough to make any economic sense, right? So the cost per measurement site that you are measuring needs to be not grossly more expensive than alternatives.
Right. And so, talking about CFAT, right? What, when was that on the roadmap? It's like 2030 or something?
Yeah,
Uh,
2032, somewhere to be
Yeah.
in high volume, but you will. So the way that our customers typically work is basically whatever works in research moves to ramp. Whatever works in ramp moves to high volume. So you have to go in early as a process
Yeah.
of getting developed to have your customer gain trust and get to use the thing to make sure that you actually are bringing the information content they need. So yeah, if something is going into HVM in 2032, then you got to count back several years for when you really want to have
Right.
a tool in their hands.
And what's that relationship with the customer like? I mean, how intense does it get, right? I mean, for them it is, do or die basically, right? So they're really working to find this process in R&D and then scale it out. So you have to be there, and they want something from you. Uh, what is that like?
Yeah. Yeah, so I would say, well, collaborating with customers has been by far the most fun part, of
Ah,
this
yeah,
this whole experience, over the last 10 years. So I think it is a huge pleasure to get to go work with these groups because they are super knowledgeable. They are in some ways so much more knowledgeable, about metrology than any metrology vendor can ever be because they're really on the floor, they're really, like, fighting with the tools, they're really, at the most advanced, pain points, and
right.
they
They're the end users. Yeah.
yeah, yeah, but the quality of these scientists is not to be underestimated. So that has been, I would say, the fun part, is getting to work with them to understand where their pains are and to try to help them, and to try to explain, like, as, like, transparently as we can, what we're doing and why it makes sense or why we think it makes sense, and ask for feedback and ask for what we should be doing.
Hmm.
That's how you get better. That's how you make something that actually has value to them.
Yeah. And what do they expect from you that might have surprised you?
Uh, I don't know if it's a surprise.
I mean, let me give an anecdote from Ari Den Boef, right? This fellow at ASML. I've had the pleasure. We of course both have worked at ASML. I still work there, um, uh, and one of the anecdotes that Ari has told on the public stage quite often is that he had the idea, this concept of UTstar, our optical metrology tool, in his mind, and he went to customers and learned at customers that there was a different use case that he had imagined, right? So, and that's what he ultimately went to work on, and that's what brought the success of UTstar where it is today. Um, that's what I was thinking about when I asked this question.
Oh, yeah, very good point. Yeah, so that literally happened, for us. So, we as ASML started on overlay. Because
Ah,
ASML is a lithography company, and ASML therefore likes to measure overlay because it's a main knob that they can turn on the scanner. And that was in the beginning all that we were doing with stock X-ray. And then we went out to customers and showed them this nice overlay thing, and they said, "That's great, lovely, but there's other tools in the world that can measure overlay. What we don't have any other tool in the world to measure is the 3D profiles of on these
right.
cases, like gate all around." And yeah, we resisted for a while, and then eventually it was so clear that this was really what they were all screaming for that we took a hard left turn and started to develop this 3D profile metrology thing. And yeah, well, ultimately that was farther away from ASML's core business than optical, and ultimately that is a big part of why we stepped out of ASML and became
Sure.
independent, because ASML wanted to focus on, yeah, the litho stuff, and the metrology for it, and yeah, more power to them. It's an amazing business, so it makes a lot of sense. But
Yeah.
yeah, for us, basically, the killer use cases turned out to be on etch control and deposition control for these advanced 3D geometries that stopped being so litho centric, and yeah, that eventually fueled our separation.
Yeah. Yeah. And yeah, I mean, also in light, of course, of the AI era, which is chock full of all these 3D stacked kind of architecture. So in that sense, the timing also is really solid.
Yeah, totally. No, so the timing has been incredible for us. You have to get super lucky to basically start with something 10 years ahead of a boom that exactly at the moment when you're finishing, means that the demand for, wafer metrology goes through the roof. So
Yeah.
that's great, right? And basically, as you make these stacked 3D devices, you just have to stack more and more wafers on top of each other, and the number of measurements of each wafer, well, it's linear in the number of wafers. So,
Right.
uh, yeah, obviously, right? But that has been really convenient, right? At this moment of becoming this enabling thing for AI infrastructure. At the same time as we manage to bring this tool to a level that it could actually help.
Yeah. And it's been spotted because, of course, you've raised 20 million euros, oversubscribed the seed round. So here you are building this tech, building your team, building your company. Walk me through what a typical week for you looks like right now.
Yeah, so, busy, right? I think any founder will say really busy. I am, well, spending a lot of time growing the team, spending a lot of time getting ourselves put back together in terms of being able to demonstrate our technology in this new setting. We had to move our tool, out of ASML and into a new clean room and get it back up and running again. So that's on the technical side, a lot of what we're doing. I am traveling. I'm going to see customers. I am going to conferences. I am talking to investors, of course, because yeah, we this is a very expensive hobby. So we we've raised 20 million euros, and that's great. But there shall be more. So uh, yeah, that is always on the mind when you are the founder of a startup, I think. And but yeah, we are here in our office in Eindhoven, and it really begins to feel properly like a company, and like we're able to start focusing on technical and not only on the super basic operational, like we need contracts and all that kind of stuff. We managed to move past that zone.
Right. I'm having sort of a flashback to the early days of ASML, right? And there's this nice anecdote from that time. I think it was the first CFO, Gerard Verdonschot, who said something like in an interview, they called us the cowboys of Veldhoven, right? Referring they being Philips. And I think for him and that early team, it was a very cautious choice to be different from where they came from, right? So the natural question then becomes, what will you be doing differently at Envisix?
Now, yeah, so part of the answer is, I think, true of any such situation where you step out of a parent company and you try to make a new thing in a small organization, right? You try to be really lean, you try to be really efficient, you try to be really process light, and you have the luxury of being really process light when you're small.
Yeah,
And I think, yeah, ASML necessarily had to become a huge company to make a huge tool that is reliable and to make sure that the next one is the same as the last one, right? That requires you bake in a lot of process, requires a lot of alignment, a lot of meetings, a lot of documents. So
yeah,
uh, I think we are at a phase in our development where we can be much more process light. We can really act like cowboys. We can really go try stuff really quickly. We can respond to customers asking, can you try this? And the answer is yes. Not. I need 1,000 meetings to think about it. And yeah, we're trying to keep our people's agendas as empty as possible so that they have the freedom to, really do their work. And
right.
of over time, this will grow, and necessarily, this is just the lifespan of a company, right? But we're in the fun early cowboy part. I definitely recognize that feeling. So.
Yeah. Let's look into the future then. In a few years' time, where is soft X-ray metrology and what does Envisix look like?
Yeah, so, well, I mean, step 1 is get a first version of a tool out, into the hands of our customers, make sure that everybody early in their process development can, use one and begin to gain trust on the information. But then step 2 is scale that up, and make sure that if they wanna order 10 or 20 or more, then they can. So we need to, yeah, work with really good contract manufacturers to build at scale and to make sure that our organization is there and ready in terms of customer support and all of these organizations that have to grow to really be a solution and again, not just a science experiment. And then I think there's a lot of possibilities as well for diversification here. So if you think about all of the applications that were found for the laser, right in the last 70 years, there have been so many areas where new light sources can be helpful in diverse ways. And I think we already have a pretty long list of ideas of how you might diversify using this short wavelength laser like light source, right? So we're trying not to be a one hit wonder. We're trying to be a whole class of useful short wavelength laser driven tools.
Awesome. And in terms of soft X-ray, the tool basically, right? What is the timeline? What does the timeline look like? Are there already tools at Chipmakers?
Yeah, so I'm not going to say that. I'm
Okay,
sorry.
good.
uh, don't want to reveal too much about exactly where we are. It is not too long now, I would say,
Good.
until we have a product in our customers' hands. But the shipping date we're going to keep to ourselves for the moment.
Awesome. Awesome. All right. Well, let's wrap up. Christina, thank you. It was a real pleasure. And folks, for more information about our company, Envisix, simply go to envisix.com. There's also a nice little technology explainer there, which you can take a peek at. And to stay up to date with the know how and wow of science, tech, and chips, you know where to go. This is Always Be Curious. And that's the show for this week. My name is Sander. See you soon. So, yeah, you should